In the previous slides, we demonstrated an example of how to compute confidence interval estimates for the mean of a population whose standard deviation is known. But in most sampling situations, the population standard deviation is not known. Here are some examples where it is unlikely the population standard deviations would be known. The dean of the business college wants to estimate the mean number of hours full-time students work at paying jobs each week. He selects a sample of 30 students, contacts each student, and asks them how many hours they worked last week. Number 2 would be the dean of students wants to estimate the distance the typical commuter student travels to class, and she selects a sample of 40 commuter students, contacts each, and determines the one-way distance from each student's home to the center of campus. A third way would be the director of student loans wants to know the mean amount owed on student loans at the time of his or her graduation. So the director selects a sample of 20 graduating students and contacts each to find the information. So how do we estimate the population means for these examples? We explore the procedure for estimating the means when the population standard deviation is not known in the next few slides. This procedure uses the t-distribution. In computing a confidence interval for the mean of a population, when the population standard deviation is not known, and when the sample size is small, assuming the sample comes from a normal population, the appropriate distribution to use is the t-distribution. So the t-distribution is like the z-distribution in that it is also a continuous distribution, bell-shaped and symmetrical. However, as illustrated on the figure in this slide, compared to the normal distribution, the t-distribution is more spread out and flatter at the center. As the sample size increases, however, the t-distribution approaches the standard normal distribution. So for sample sizes larger than 30, the z-distribution may be used instead of the t-distribution in computing a confidence interval for the mean. We compare the z and t distributions when the sample size is small using the chart on this slide. Notice that for a given confidence level, say 95%, the value of t compared to z for a sample size 5 is much larger. For this instance, the value of t is 2.776, while the value of z is 1.96. This illustrates that the t-distribution has a greater spread than the z-distribution for small samples. Consequently, the t-distribution will yield a larger margin of error than the z-distribution for the same level of confidence. However, as the sample size gets bigger, the value of t gets closer to the value of z. So as such, the margin of error that results in computing a confidence interval estimate for the mean of a population when using the t-distribution will be almost the same as the margin of error when the z-distribution is used with large samples. Let's now look at an example of how to use the t-distribution in computing a confidence interval for the mean of a population whose standard deviation is unknown. A tire manufacturer wishes to investigate the tread life of its tires. A sample of 10 tires driven 50,000 miles revealed a sample mean of 0.32 inches of tread remaining with a standard deviation of 0.09 inches. Construct a 95% confidence interval for the population mean. On this slide, we summarize the given information in the problem. The sample size n is 10. These tires were driven 50,000 miles, has an average of 0.32 inches of tread remaining. This is the x bar. The standard deviation of 0.09 inches is a sample standard deviation, so we designate this as S. To compute the 95% confidence interval for the true mean tread thickness, we will be using the t-distribution since the population standard deviation is not known. But before we apply this formula to compute the confidence interval, let's see how we obtain the t-value for a 95% confidence level. We'll demonstrate this on the next slide. To obtain the t-value for a 95% confidence estimate, we look at the t-table given a 0.05 level of significance for a two-tailed test, or simply looking up the 95% confidence interval and the degrees of freedom of 9. Remember that the degrees of freedom is obtained by subtracting 1 from the sample size. It is 10 minus 1. So for 9 degrees of freedom and a confidence level of 95%, we obtain a t-value of 2.262. We substitute this back into the confidence interval formula as shown in the next slide. Substituting the given information into the confidence interval formula, we obtain a lower limit of 0.256 and an upper limit of 0.384. So based on this confidence interval, we conclude that the manufacturer can be reasonably sure that the true mean remaining tread depth of its tires after having been driven 50,000 miles is somewhere between 0.256 and 0.384 inches. On this slide, we summarize the formulas for computing a confidence interval for the mean using the t and the z distributions. The starting point is the assumption that the population is normal. We then ask the question, is the population standard deviation known? If the answer to the question is no, we use the t distribution. Otherwise, we use the z distribution. Both formulas have the same components, a point estimate and a margin of error. The margin of error in the two formulas is computed in a similar manner and is comprised of the same components. These components are the confidence level as expressed by z or t, the standard deviation, and the sample size.